a cosmologist is a really difficult thing in some level, because you're asking really difficult questions of the universe, and so every day you're confronting all these very confounding problems. But what you do to solve them on a day-to-day basis can involve things like just having discussions with your friends who are also your colleagues, and working with students. And quite a lot of the time we spend making computer programs which go on big supercomputers, and then you use these programs to analyze the data that we are getting from these satellites like Planck. And quite a lot of the time it can seem like it's a humdrum activity, because you're sitting at a computer coding, looking for bugs in your code, and then trying to analyze the data. But occasionally, and these are the moments you live for, you discover something or you understand something that you didn't understand before, and perhaps nobody understood before, and that's what you live for. Cosmologists are asking the biggest questions. It's quite an audacious exercise to ask, you know, how old is the universe? Where did it come from? How is it evolving? What's going to happen to it in the future? And where did all the stuff in the universe come from as well? So those are like the biggest questions, and those are questions that humanity has been asking themselves ever since we looked up at the stars and started to wonder what is our place in the universe. So most of cosmology is, most of primordial cosmology at least, is about studying what happens at very, very high energies. So in a very weird way, the very largest scales we see in the universe are related to the physics that we can probe only at the very smallest scales. Because when you probe physics at very, very small scales, you are probing higher and higher energies. And the early universe was a place which was at very high energy. It was actually very small. It's since expanded to enormous scales, but it was very small back then. And the physics that happens at very high energies therefore controls how, for example, all the structure in the universe was originated. And the best theories for the origin of the structure in the universe involve scalar fields. And it is quite a dramatic leap in physics to postulate the existence of scalar fields. So the Higgs field represents the first discovery of a fundamental scalar field in nature. So it's really great to have an actual concrete example of one in nature, because we know now that we are on the right track. So the Higgs discovery, for me personally as a cosmologist, was a sign that, you know, the thinking in the last 20 years of what is the physics that, you know, sourced the Big Bang is on the right track. And then when the Planck data came in, the Planck data now very strongly indicate that these theories, it's called inflation, which is another kind of scalar field, that this inflation is probably on the right track to answering the question. So scalar fields, we see them now in nature, and there's quite strong evidence that they probably existed in the very early universe. So these two things are coming together in a very nice way, and that is personally very exciting. In terms of looking at the Planck data as it came in, it's just stunning. I wasn't there right at the start of CMB observations, but I started my career essentially with the previous CMB satellite called WMAP, which was the second CMB satellite. And that was a revolution in cosmology in itself. But the quality of the data from Planck, when you look at it compared to what we saw coming in from WMAP, is stunning. It's because, of course, the technology has improved dramatically in the meantime. But I remember the first Planck data that I saw, and it was from the first 2-week survey that they did. And when you just plotted it without doing really anything to it whatsoever, you could see the CMB peaks in a really nice, regular way. And having been used to looking at data of less high fidelity, it's just like, wow, I couldn't wipe the smile off my face for a week. And so from the point of view of just looking at the data, it's just really beautiful. And I think we're just starting to explore what we can learn from it. So already there are these conclusions about the physics of the very early universe. But Planck has also opened up other frontiers. So for the first time, we can make full sky pictures of where all the matter in the universe is. And we do that using another type of observation which we can extract from CMB data, which is that the CMB photons, as they pass around very large structures in the universe, like clusters of galaxies, they're full of dark matter. And this dark matter slightly deflects the path of the photons, and that makes a little effect on the temperature maps that we look at from Planck. And because this little effect is present all over the sky, we can reconstruct where all these big structures are and make a map of all the dark matter in the universe all the way through cosmic history back to about 13 billion years. And this is a new type of observation that links CMB data from the early universe to galaxy surveys, for example. We can figure out how particular types of galaxies and structures that are made of galaxies are forming and evolving with the help of this data. And it's one way to probe this dark matter directly, because of course it's dark, we can't see it. We can only see its effect through other ways, like this deflection of the CMB photons. So for a long time, we have been forced to assume that the observed light from galaxies trace the underlying dark matter, but now we can directly see it, and that enables a lot of astrophysics that wasn't possible before. So that's also personally very exciting for me.